Section 6, Package Management and Software Installation. Let's go back to the 1990s and look at where the name Dependency Hill actually came from. Back then, installing software meant the standard 3-step source tarball routine: /configure, make install, compiling everything by hand the whole way through. This approach had two fatal flaws. First, there was no record of anything. Files got scattered across the whole system once installed, and later, removing it meant manually guessing what had actually been put where. Second, dependencies had to be tracked by hand, one by one. Which version of which library does this program need? And get one layer wrong and the whole build fails outright, sometimes without even a clear error. The solution distros eventually landed on was a 3-piece system: a package carrying its own metadata, a database recording which files belong to which package, plus a centrally distributed, signature-verified repository. At this point, you might reasonably ask, so why does today's development environment still turn into such a mess so often? Because the package system and development needs fundamentally want opposite things. The package system optimizes for system-wide consistency and stable versions. One change affects the whole machine. Development work, on the other hand, often needs the very latest version, sometimes a completely independent version per project, and ideally installable without root at all. Those two needs don't line up, so each programming language ecosystem grew its own dedicated package manager, none of which know anything about each other's bookkeeping. Let me just read you the handout summary directly. It's precisely put: today's mess comes from several systems that are each individually sound in their own logic, stacked onto the same file system, with no awareness of each other's existence. On the Ubuntu side, the bottom layer is dev-nd package. A dat file actually splits into two parts. The control part holds metadata and maintenance scripts, and the data part holds the actual file tree that gets laid into the root file system. When dpackage installs something, it lays down the files, registers them in the database under /var/lid/dpackage, and runs whatever scripts need to run. But there are two things it flatly refuses to do. It won't go download anything off the internet on its own, and it won't resolve dependencies for you. Those two jobs belong to the layer above it. That layer above is apt. Sudo apt update only refreshes the local index listing. It doesn't actually upgrade anything yet. Sudo apt upgrade is what actually upgrades already installed packages. Sudo apt install does dependency resolution, downloading, and signature verification all in one go, and only then hands things off to dpackage to actually lay the files into the system. Let me add a good pre-install habit the handout doesn't specifically call out: apt search plus a keyword to find a package, apt show plus a package name to see its version and description. Check first before you install. Don't just copy-paste whatever command a random tutorial online tells you to run. Auditing works in both directions. Dpackage. L checks which files a given package actually owns, dpackage. S goes the other way, checking which package a given file belongs to. If dpackage, I get stuck halfway through with unresolved dependencies, sudo apt f-install can usually clean up the mess. That two-way auditing is really the core value the whole package system provides, and the cost is that versions run a bit old, and the whole machine can only have one version installed at a time. What do you do when the version's too old? A lot of online tutorials will tell you to add a PPA, a personal package archive. Plainly put, a third-party software source maintained by some individual. It works, but you need to understand what it is. You're essentially writing whatever this person publishes going forward directly into your system's trust ledger, a trust level one notch below the official repository. Before adding one, it's worth pausing to think about who this maintainer actually is and whether they're worth trusting. The first stop in language ecosystem territory is the pip disaster zone. Pip and apt both think they're the ones managing your Python packages. Run sudo pip install, and you end up with two ledgers that no longer agree with each other at all. On newer Ubuntu, running pip install directly gives you an error saying externally managed environment. That's the system deliberately designed to block exactly this kind of accident. There's really only one correct path: install Python inside of venv or install at the user level, never touch the system's copy. For this course, we recommend UV. UVVNV creates a clean, independent environment. UV add numpy installs a package into that environment. UV tool install rough is for installing the kind of tool you want available globally. The bookkeeping stays perfectly clear from end to end. 3 practical tips here. First, a habit for auditing yourself. Once a venv is activated, run which python3, the path it prints, should land inside your venv folder. Second, the uv.lock or requirements.txt file at the root of a project. Its real value is reproducibility. With that file, someone can reproduce the exact same environment on their own machine. Whether your thesis experiments can be reproduced by someone else often starts right there with that file. Remember to commit it into your Git repo. Third, a lot of research fields default to conda, and it works on the same logic. But within a single project, never mix conda and pip installs. The two ledgers will overwrite each other's records, and once that breaks, it's extremely hard to untangle. Usually by the time you've dug halfway through, you just want to delete the whole environment and start over. The cargo world takes a different path entirely. Cargo install downloads the source code and compiles it locally, dropping the resulting binary into ~/.cargo/bin. Binaries built with Rust barely depend on external libraries, so there's no need for anything like Python's isolated environment dance. You can check the ledger with cargo install list. npm install, g, and go install are variations on the same theme. The shared spirit across these language ecosystems can be summed up in 3 phrases. Install under home, don't touch the system's territory, no sudo needed. The real high-risk zone is elsewhere, sudo make install. C and C++ have no official default package manager, and to this day a huge number of projects still get installed from source the old-fashioned way. And what gets installed is often a system-wide shared library, so when something goes wrong, the blast radius is the whole machine. There are 3 disaster scenarios here you should be prepared for. First, there's no ledger at all. The only receipt, install manifest.txt, sits alone in the build directory, and once that directory gets deleted, the receipt is gone with it. Second, /usr/local/lib takes priority over /usr/lib, so a manually compiled lib opencv will straight up shadow the distro's own copy. And every program on the machine that uses that library suddenly starts loading the wrong version. Third, an accidental prefix into /usr will collide with files apt manages, and both sides end up thinking they own that territory. 4 correct habits, follow all of them. If a package already exists, use the package, don't compile it yourself. If you genuinely have to compile from source, add -dc make install prefix to your cmake command and point it at .local under your home directory or install it versioned under /opt. Keep a receipt or use a tool called check install, which packages your build output into a dev file so dpackage can keep the books for you too. And the cleanest option of all. Don't install it at all, link against it directly from the build tree, or just throw it in a container entirely separate from the host environment. The loose binary crowd you just need to recognize by name, grab a pre-built binary or an app image and drop it into ~/.local/bin. Updating is on you. The curl pipe bash pattern, a one-line install that runs the whole thing in one go, is how both RustUp and UV officially ship. Here's a safety habit I'd recommend building. Before you pipe something into bash, open that URL by itself first and actually read through the script with your own eyes before running it. It's about to do whatever it wants to your entire machine. Spending 30 seconds looking at what it's actually planning to do is not excessive at all. Snap and Flatpak take the sandbox route instead, deliberately keeping themselves at arm's length from the rest of the system. And to close it out, containers. Once you're inside a Docker run, you're in a completely separate world with its own /usr/bin and its own apt ledger. Its answer to dependency hell is remarkably blunt. Don't bother resolving the conflict, just make sure the 2 environments never meet. ROS binds itself very tightly to a specific Ubuntu version, and the standard practice in a lot of labs is to keep the host machine clean and do all development inside containers. We'll spend a whole session on that next week. Here's a one-line summary table to keep in mind. apt manages territory under /usr. With dpackage handling the bookkeeping, UV or pip with VNV manage the VNV folder and ~/.local, with the rule being never use sudo. The cargo family manages its own bin directory under home. Make install must always set a custom prefix and leave a receipt. Loose binaries keep their own books. And Docker packages the entire world into an image. 6 approaches, each with its own territory and its own ledger. Mixing them is exactly where the mess comes from. Section 7, Path and Environment Variables. This is the centerpiece of the whole handout. Everything planted in earlier sections gets paid off right here, so stay sharp for this one. Let's start with a classic symptom. Later on, once you get into the ROS2 portion of the course, every time you open a new terminal, you'll have to source /opt/rossetup.bash and then source your own workspace's install /setup.bash. Both steps every single time, no skipping either one. Skip those 2 steps and 3 symptoms are waiting for you. The ROS2 command says, command not found, or it says package not found, even though you just successfully built it, or the program runs. But it's running an old version, and you spend forever confused why nothing seems to have changed. All 3 symptoms trace back to environment variables. Let's solve them one at a time. The mystery behind symptom 1 is path, and the rule is 1 sentence. First match wins. The shell never searches your entire disk to find a command. That would be far too slow. It only looks at one environment variable called path, run echo path, and you get a long list of directories separated by colons. The shell scans them left to right and stops at the first match. It doesn't keep looking after that. ROS2 gets installed under /opt/ROS, and its bin folder isn't in that path list by default. The program itself is sitting right there on disk. It's just that the lookup list has no entry pointing to its address. The first thing setup.bash does is add that address into path. While we're here, let's answer a question you probably already wondered about. Why isn't the current directory in path, so that running your own program still requires you to type out /program explicitly? That's actually a deliberate security measure. Suppose path really did include the current directory. Someone with bad intentions could drop a malicious program disguised as ls into a shared directory. You cd into that directory, casually type ls to look at the files, and you've actually just run the malicious program instead. This kind of attack isn't rare at all in security circles. So that slightly annoying .flash you have to type is actually there to protect you. 3 tools for investigating, which ROS2 shows which one the shell would actually pick. Type A, Python 3 lists every candidate sharing that same name, and if you've installed the new version but keep getting the old one running, use #r, which clears out Bash's own memory cache of where it last found things. It often keeps remembering an old address and won't let go. Setup.bash touches far more than just path. This table is worth writing down. Path, which the shell uses to find executables, and prefix path, which ROS2 specifically uses to find the package index. That's actually the answer to symptom 2. That index doesn't have your freshly built workspace registered in it. Python path, the path Python checks to find modules, LD library path, where program looks for dynamic libraries at launch, and C, make prefix path, the path used at build time to find dependencies. All of these are environment variables, fundamentally just a set of key value pairs that travel along with a process. So the real question is, what actually makes them travel along? This is where we circle back to something from your OS course. Remember that a new process is born through 2 operations, fork and exec. Here are 3 rules to memorize. Environment variables live in the process's own memory space, and fork makes a full copy of them for the child process. Exec swaps out the entire program. But by default, the environment variables come along unchanged. They don't get wiped. Whatever the child process changes afterward in its own copy never touches a single byte of what the parent process is holding. The keyword is copy, not share. Hold on to that phrase because several later mysteries get solved by it. The whole process tree is really just an inheritance tree of environment variables. The root of that tree is systemd, PID1. One branch is the chain from logging in, opening a terminal, and running bash. Everything you normally source lives on that chain. Another branch is whatever process SSHD or cron spawns. They have zero awareness of anything you did on that other chain. The 2 chains never touch. Scenario 1. First, why do you have to use source and can't just execute the script directly? Running bash setup.bash forks off a separate child shell, and the variables get set on that child shell. The moment that child shell exits, those variables vanish along with its memory, completely wasted effort. Source doesn't fork a new shell at all. It's the current shell itself executing the script's contents line by line, so the variables get written onto itself, and that's what actually makes it take effect. This also happens to explain why you have to resource every time you open a new terminal. Every terminal window is a brand new process being born, and its environment variables are a snapshot copy from its parent process at the exact moment it was born. By the same logic, once you edit ~/.bash_rc, any terminal window that's already open won't automatically pick up that change. You either need to open a new terminal or manually run source ~/.bash_rc in the existing window. A lot of people edit a config file and wonder why it's not taking effect. It's usually just that the file hasn't been reread yet, not that the setting itself is wrong. Scenario 2, switch to a different chain and things break entirely. A node that runs perfectly fine when you launch it in the terminal gets rewritten to autostart at boot, or run remotely over SSH, and it just dies. The first half of the diagnosis is about the inheritance chain. Processes spawned by systemd and cron trace their ancestry straight back to PID1. Their parent chain never passes through your interactive shell at all, so anything you sourced in your own shell is completely invisible to any process on that chain, which means a script that auto-starts at boot needs to resource whatever it needs itself right at the top. Or better yet, use the environment and environment file fields in the service config file to spell the environment out explicitly. Keep the names of those 2 config fields in mind. Next section, when we get to systemd, you'll see exactly which file each one belongs in. The second half of the diagnosis is about which files get read, and when a login shell from SSH or a TTY login reads ~/.profile or ~/.bash profile. Opening a terminal inside a desktop environment counts as interactive non-login and reads ~/.bash rc. A non-interactive shell spawned by systemd generally reads none of those config files at all. The practical rule, put your environment settings in ~/.bash rc and make sure ~/.profile sources it. Ubuntu's default configuration already has that line in place. Let me add one more absolutely classic self-inflicted disaster. Export path equals a double quote, new directory, then $path again. Miss that trailing $sign path at the end, and the whole search path gets wiped clean. Even ls turns into command not found, and it looks like the entire machine just broke. If this actually happens to you, don't panic first. Most commands still work if you call them by absolute path, like /usr/bin/ls, and just opening a new terminal fixes the whole thing automatically, because you only broke the copy that one specific process was holding. Every other process's environment is completely untouched. That's exactly copy, not share, quietly protecting you again. Scenario 3, export in parallel worlds. A shell actually has two kinds of variables. A plain shell variable only lives in that shell's own variable table and never gets handed to anyone else. Add export, and it gets placed onto the handoff list, passed along to any child process forked afterward. Write ROS domain ID equals 42 without export, and the node simply can't see that setting at all. You have to add export for it to actually get passed down. Two terminals, one with the export and one without, and the nodes running in each one live in two mutually invisible parallel worlds. ROS2 topic list can't see across them. On the surface, it looks like a network problem, but really it's just that the two shells' environ contents differ, nothing to do with the network at all. Investigation tools, NV prints out every environment variable currently set, pipe it into grep ROS to filter down to what you want. Print NV plus a variable name checks a single variable's value on its own. And if you just want to change something for one run without touching the whole shell settings, you can write ROS domain ID equals 1, a space, and then the command right after it. That only affects that single execution, without polluting the shell itself. It's especially handy for testing what effect a particular setting has. Symptom 3, running an old version, is solved too now. A workspace's own setup script stacks its own path in front of /opt/ROS. In the ROS world, this is called an overlay, same rule underneath. Pat is first, match wins, whatever's listed earlier gets found first. Python VNV's activate does essentially the same trick. Fundamentally, it just inserts the VNV's bin folder at the very front of path. You're fully equipped to verify this yourself right now. Run echo path before and after activating, and compare the two results side by side. Whatever new segment shows up at the very front of path is exactly what VNV just quietly inserted.